We're going to look at a whole unit starting now about graphing and the derivatives. This first one is called interpreting graphs, and we'll look here at the rise and fall of a graph. Now, there are three things to think about when you think about graphing. We think about our output values. The y values are the f of x values. And the y values can either be constant, and if the y values are constant, that means the graph is a horizontal line. Horizontal line. Constant y values. If the values for y increase, then the graph rises. So if the y values are getting bigger, as you connect those dots, the graph rises. And if y values decrease, then the graph falls. Okay. Now, in calculus, we don't often talk about rise and fall. We talk about increase and decrease. So as we look at this graph, we want to know on what intervals is the graph increasing and decreasing. And so we're talking about the graph itself, and we want to know where is it increasing and where is it decreasing. And we talk about intervals mean between two x values. So if I look at the graph and I follow where the y values increase, that is the same as when the graph is increasing, and that means we look at it and it's rising. So I start here, let's say we start at 0 and it's going up, so that's increasing up to about this point up here. Now we have to estimate quite often. So this high point looks like it might be about 0.7. So it increases from 0 to 0.7. And then from there, the graph falls, decreases down to about this point, which looks like it might actually be pretty much 2.5, maybe 2.6. So it also increases from 2.6 to wherever this ends over here is about 3.5. So that's where the graph is increasing. Where is it decreasing? Well, probably everything else. It drops down to here, and it looks like it really levels off a lot right here. Let's say to about that point, it's leveling off, so that could be at maybe 1.8. So starting at 0.7 to about 1.8, it's definitely decreasing. It's a little flat, but it's really not a line. And sometimes when you look at something on a computer with the pixels, it looks totally flat. Generally, with a function, it's not going to be totally flat unless it's piecewise. If we have one thing that says f of x equals, we're not going to have flat pieces. So the pixels may look flat, but even though this looks like it flattens out about 1.8, it doesn't really. It continues to decrease till we get down here to the bottom, which we guessed was about 2.6 before it started to rise again. Let's look at another interval. Let's think about this interval a minute. Think about the interval, and please notice when it says interval, it is an interval of x's. It's not a point. It's not the point when x is 0 and y is 0.7. These are x intervals. On the interval from 0 to 1, if I start at 0 and I go over to 1, my graph increases and then decreases. So on that interval, it's neither. And so we say on this interval, it is neither increasing nor decreasing. And often instead of just saying neither increasing, it'll say neither strictly increasing nor strictly decreasing. Because when I said increasing here, that is strictly increasing. That's the only thing it does. This does not just do that. So this is some other terminology that you want to become accustomed to. In this part of our interpretation of graphs, we're going to look at concavity. This graph is concave up. With graphs in math, we talk about them being either concave up or concave down. We don't have concavity, concave, and convex. So this graph is concave up. And let's see what that means by looking at the slopes of the tangent lines. Remember that the slope of a tangent line is of a derivative, and so that is what we concentrate on in calculus, derivatives in the slope of a tangent line. So the slopes here, remember we read left to right, so if I think about the tangent line right here, it's negative and it's pretty steep. So I would say this is a big negative number. As I move down my graph, when I get down here, that line, that tangent is not as steep, so I would call this a small negative number. So as it moves from left to right, the slopes of the tangent lines go from large negative to small negative, so that would be increasing as we move to the right. At the very bottom, we could say that it's 0. And then as we move towards the right, this tangent line has a positive slope, but it's a small positive slope. Small positive, and then as we get up here, it's very steep, so that would be a large positive slope. So for a function whose graph is concave up on this interval, we would say that the rates of change increase from left to right. And so the rates of change increase means that the slopes of the tangent lines increase. And notice that the slopes of the tangent lines lie below the graph. This is concave up. It bends up or cups up. And I tend to abbreviate concave up as, that's the C dot up. Doesn't look like a C, does it? Concave up. It cups up, it holds water. In the lessons, the description and the graphs show you concave down and then say concave up is similar. So I'm showing you what concave up means and saying when you get to the lesson and you look at that, you should have seen that concave down is the opposite of this. Now let's look at some other graphs that show concavity. A little bit different, more complicated than this one. Now this function doesn't just go all up or all down. If we look at this graph, if we look at tangent lines as we move from left to right, down here my tangent line is positive and very flat. So this is a positive slope, but very small. As I move to the right here, it's still a positive slope, but it's a whole lot bigger. Small, big. So it's getting steeper, and that increases from left to right. So this part of the graph is concave up because of the way the slopes increase. However, as I get to the middle here and then continue to the right, up here I still have a positive slope and it's large. But as I move over here further, I have a positive slope, but it's small. I almost drew that one horizontal, but it's a positive slope. I'm saying that. So here, my slopes decrease And as my slopes decrease, this part is concave down. Now in the middle, as my slopes or my rates of change got very steep and then slowed down and leveled off more, this being the steepest part, right in the middle here, what we say is that the graph increased the fastest. It was concave up, and it got very steep. The rates of change increased, but then as we passed the center point, it was not quite as steep, and the rates of change began to decrease. So this is the steepest part where the rates of change increase the fastest. The graph increases the fastest. It's the steepest. And that happens when you go from concave up. At the very change to concave down is the steepest. Notice that the whole graph is increasing, but part of it cups up and the other part cups down. Let's look at another graph. This graph has more ups and downs and little changes in the way it curves than previous graphs. So let's look at this and try to determine where it's concave up and where it's concave down. And when I say, where is it concave up, then that means we look for intervals of concavity. Where is the graph concave up and down? And where are intervals? So let's first decide where the graph is concave up. Concave up. Concave up means it bends up, it cups up. Well, as I move from left to right, if I look at the slopes of the tangent lines here are cupping down. The tangent line slopes go from steep to not so steep, and the slopes are positive, so they're decreasing over till I get to about here, and you can just look at the way it cups down. But when I get into this little spot here, it begins to turn up until about here. And then in here, you'll note it's cupping down again, but down here it's up. So somewhere in the middle, maybe about here, it changes from cupping down to cupping up. So the intervals where it's concave up would be this little piece in here. So if this is, say, -1, and this is +1, then it looks like it's concave up starting here, maybe about 0.3. So my interval would be from about a -0.3 over to 0. It cups up just to there, switches to down, starts again over here, which looks like I'm going to call it a +0.3 until the graph ends. If this is 1, we'll say that's 2. So that's where it is concave up on those intervals. For concave down, starts over here, and I'll call that -2, all the way over to this point here, which we already said was a -0.3. Changes to up, and then from 0 over to this point, which is a +0.3, is concave down. Now, it's very, very flat in the middle. Pixels are going to make it look flat, but remember that it's not really flat if it's a nice smooth curve that's continuous like this. So our intervals are concave up and concave down. But this one little spot in the middle where it looks so flat, if we think of slope, what we could say is the slope at x equal to 0, which we could write as f prime of 0 is equal to 0. So the derivative at that point is 0, which indicates the slope is 0 because it looks very horizontal. And that's one reason why these are open intervals, because we're not sure exactly what's going to happen right at that point. So this looks at the concave up, concave down, at a point where we may have the derivative at that point equal to 0. We're now going to take another look at vertical and horizontal asymptotes. You've seen them earlier in the course, but we want to emphasize them now because we are interpreting graphs, and we'll see a lot of everything that you've seen before. I dotted in the asymptotes, so when you look at these from your experience, you see I have dotted lines at x equals -3 and x equals 3. So you would say that we have vertical asymptotes at x equal to -3 and at x equal to +3. But look, it touches the vertical asymptote at 3. Well, does that mean it cannot be a vertical asymptote when x is equal to 3? No, let's think about the definition of what a vertical asymptote is. To have a vertical asymptote at x equal to c exactly means that the limit as x approaches c from either the left-hand side and or the right-hand side, either one or both of the function, is equal to either positive or negative infinity. So we're getting close to x equal to 3, and on the left-hand side, the y values, what the limit equals are the y values. These y values are approaching negative infinity. As x approaches c on the right, they're not. They're approaching whatever this y value is. It looks like maybe it is 3. 1, 2, 3. So from the right-hand side, x equal to 3 is not a vertical asymptote, but from the left it is. So that is a true statement. And as x approaches -3 from both the left and the right-hand side, we do have y values that approach negative infinity and positive infinity. So it is okay to touch a vertical asymptote. What that means, though, is this is not a function with one simple formula. It would have to be piecewise, possibly even 3 separate pieces to take care of the asymptotes as they are. Well, now, let's look at the horizontal dotted line, which would be our horizontal asymptote. Looks like that is at y equal to 1. Vertical asymptotes go through vertical values, x numbers. Horizontal asymptotes go horizontally through y values, so this looks like y equal to 1 is a horizontal asymptote. But wait, we crossed it right here. So think of the definition for horizontal asymptote. Horizontal asymptote at y equal to d says that the limit as x approaches plus or minus infinity of the function is equal to d. The function values as you go from one end of the graph to the other end, either one side or the other or both, levels off at a y number. And this levels off on both ends at y equal to 1. So we do have a horizontal asymptote at y equal to 1. Whether or not the graph actually crosses it somewhere in the middle is irrelevant. What happens at the ends as x approaches plus or minus infinity. So this is one of those graphs that you really have to think about when you see things like this, to think about what the definition actually means for a horizontal and a vertical asymptote. Here we want to look at something called the absolute extrema of the graph. Extrema means maximum points and minimum points, high points and low points. So if I look at this graph, there are 2 things I have to think about. I want to know about the absolute extreme value and the absolute extreme value of of a graph, let's say absolute maximum value is the biggest y value. Because when you look at a graph, you have x values, and each x that you plug in gives you a y value. So the absolute maximum value is the biggest y value. When I look at this graph, reading left to right, the graph starts down here and it goes up to this point, which is pretty high, but it dips and goes again to this point, and this dot here means that the graph stops. So when it stops here, clearly that is the biggest y value. So my absolute maximum value for that function is the y value, y equal to 8. Okay. Now, if I want to know about the second thing, is the absolute maximum point. And that absolute maximum point is the point C f of c. So wherever the x value is, the y value at that point. Here, it looks like when y is equal to 8, that came from x equal to 2. So the maximum point is the point to 8. There is no absolute minimum point because there is no minimum. It doesn't ever end. It continues. It starts way down and it goes up, down, and then back up to this maximum. So there is no absolute minimum for this graph. Not a minimum value or some point that is the lowest point, because it is always lower than your lowest point that you pick. Okay. So this is what we have for an absolute maximum, and this doesn't have an absolute minimum. So let's look at a couple of other graphs. Now we look at this graph. If I want to find absolute max and min points, I start down here, and that's not terribly straight, but almost. This point is lower than this point. So that point, whatever the y value is, let's say -3, this is the absolute minimum. It equals -3. And it occurs at x equal to -2. That is the absolute minimum point. This point is lower than that point. My absolute maximum point, well, looks like this point is the highest. Note that there are dots on each end, so it stops. This does not continue to go higher. So it looks like this point up here is my absolute maximum. And my value would be, how does that compare? 4? The absolute maximum is y equal to 4 at x equal to -0.8. So I have an absolute maximum point. I have an absolute minimum point. This also happens to be an end point. That's fine. Let's look at one more graph. So this graph doesn't have any dots to end anything. So we would say the pattern continues so that it does not stop at either end. It continues going up. So I don't really have an absolute maximum. No absolute max, because it continues going forever and forever. What about an absolute minimum? Well, let's see. It actually looks like I have 2 points with the same y value, and they are the lowest y value. But remember, the absolute max or min is a y value. So my absolute minimum on this graph is y equal to -2, and it occurs twice. That's fine. You don't have just one absolute max or one absolute min. Even though it says the absolute is the biggest value or the smallest value, this is the smallest value the function attains. Doesn't matter how many times you get it. That's fine for a minimum or a maximum. But the absolute is just the absolutely the highest value or the lowest value. Here we want to look at relative extrema. And f of c is a relative maximum if f of c, the y value for the function, is greater than or equal to f of x for all x values in an open interval containing x equal to c. Well, I know that's a lot of math speak. So what that means is a relative maximum is the highest point. F of c is higher than anything around it for all x values right around there. Call that D. So if I look at a high point, here's a high point right up here. Let's look at f of a. And f of a is this point at the top, the y value when x equals a. All the x values in an interval around that point. If I go around that point, that is the highest point. Notice that means that it increases right before you get to it, and then on the other side, the graph decreases. So f of a is a relative maximum point. So we could say that a relative maximum occurs at x equal to a. How about a relative minimum? A relative minimum is that f of c if f of c is less than or equal to f of x for all x values in an open interval containing x equal to c. So let's think about f of b. Well, when we look at x equal to b and we go to the point at b, that is a low point. And so all of this math talk says that this f of b value is lower than anything else around it. And it is, because the values on this side for y, the values decrease, and on this side, the values increase. And so f of c is less than the y values in an interval around that point. So f of b is a relative minimum. So I've had a relative maximum and I've had a relative minimum. So let's come over here and look at that last point we have. The graph ends there. That's what that big dot means. It does not end over here. It just continues the pattern going down. But this point up here is f of d. So that value is f of d. What about f of d? It's high, so is it a relative maximum? Well, it's not. No, why not? Why isn't that a relative maximum? The phrase open interval. When you look up here, we have a relative maximum if we can take an open interval around our D value, and that is the highest point. We can't go around. There's nothing around this. I can't draw a circle around it. It ends there. So that f of D is not a relative maximum because that's where it ends. Now, it is an absolute maximum. Yeah, it's higher than that point. So we can say f of D is an absolute max, but it is not a relative max because the graph ends there. There is not an open interval around it. Now, some calculus books define things differently. Some define them like this. Keep in mind, this is what we use in this course. In this part, we're first going to look at inflection points. An inflection point is a point where concavity changes. We've seen concave up, where it cups up, and concave down, and the point where that changes is called the inflection point. So as I move from left to right, the graph is cupping down here. It's increasing, decreasing, so it's cupping down, maybe till I get to about this point right here. That point beyond it is cupping up, so this is an inflection point. So now it's concave up, but when I get up here at some point, my cupping up becomes cupping down. So over maybe about here, I have another inflection point. So an inflection point is a point where concavity changes. When you look at this entire graph, we could pretty much include everything in the lesson looking at this one graph. So let's see what else we have here. We just talked about this section in here is cupping down. So this whole piece would be concave down, as is this piece right here. This does not turn to go back up, so this from here over is also concave down. And this piece in the middle is definitely cupping up. So in the middle we have concave up. What else do we have here? We have high points and low points. So this would be a relative maximum. It increased up to that point and then decreased. So around this point, it's an open interval up to that value and down, so that makes it a relative maximum. And the same over here. Up to that point and then down makes this a relative maximum. I went down to this point and then up. So at this point it is a low point, but around it, it changes. And so this is a relative minimum point. I mentioned increase and decrease. So we could say that from here over to here, our graph is increasing. And then from there to this point, it's decreasing. From here to here, we're increasing, and then decreasing again. I put concave up and down on the graph, but let's look and see where those points go. From here to here, this is concave down. So if we were talking about what the interval is, we would include these x values for concave down and these x values for concave down, and then in between those x's we have concave up. What did we do that's not mentioned? Absolute extrema. So I have a relative maximum. I have a relative maximum here, but it's also the very highest point on the graph. So we have a relative maximum and an absolute max. So that point, that 1 point, is both. When I get down to the end here, that is my lowest point. And so this would be an absolute min, because it is the lowest point on the whole graph, but it is not a relative minimum, because that is the end point. The graph ends there. There's not another part to increase beyond it, so it's not a relative minimum. This point is both. This point is just a relative max. This is just a relative min. This is just an absolute minimum. And we don't have any asymptotes here, so that part of this unit doesn't really apply. But this is what everything we've done looks like on a single graph.